Okay, hi and welcome back to this video series on Cisco ASA firewalls. Network address translation. NAT. Network address translation defines a one-to-one address mapping when a packet passes through the security appliance and matches criteria for translation. The security appliance either assigns a static IP address, static NAT, or allocates an address from a pool of addresses, dynamic NAT. Cisco ASA can translate an internal address to a global address when packets are destined for the public network. With this method, also known as inside NAT, the security appliance converts the global address of the return traffic to the original internal address. Inside NAT is used when traffic originates from a higher security interface, such as the interface inside, and is destined for a lower security interface, such as the outside interface. In figure 423, a host on the internal network 192.168.10.10 sends traffic to a host on the outside network 209.165.201.1. The Cisco ASA converts the source IP address to 209.165.200.226 while keeping the destination IP address intact. The web server responds to the global IP address 209.165.200.226. The security appliance reverts the global IP address to the original internal real IP address of 192.168.10.10. So you can see here figure 423, inside network address translation, static NAT. Optionally, the host on the lower security interface can be translated when traffic is destined for a host on the higher security interface. This method is known as outside NAT. It is useful when you want a host on the outside network to appear as one of the internal IP addresses. In figure 424, a host on the outside network 209.165.201.1 sends traffic to a host on the inside network 192.168.10.10 by using its global IP address as the destination address. Cisco ASA converts the source IP address to 192.168.10.100 while changing the destination IP address to 192.168.10.10 because both the source and the destination address are changing. This is also bidirectional NAT. Port address translation, PAT. Port address translation defines a many-to-one address mapping when a packet passes through the security appliance and matches criteria for translation. The security appliance creates the translation table by looking at the layer 4 information in the header to distinguish between the inside hosts using the same global IP address. Figure 425 illustrates an appliance set up for PAT for the inside network of 192.168.10.0/24. However, only one global address is available for translation. If two inside hosts 192.168.10.10 and 192.168.10.20 require connectivity to an outside host 209.165.201.1, the security appliance builds the translation table by evaluating the layer 4 header information. In this case, because both inside hosts have the same source port number, the security appliance assigns a random source port number to keep both entries unique from each other. This way, when the response from the web server returns to the security appliance, the security appliance knows to which inside host to forward the packets. Address translation and security levels. By default, Cisco ASA does not require an address translation policy to be created when the inside machines host toward the higher security level interface due to access to hosts on the outside network, resource towards the lower security level interface. However, if a packet matches a NAT-PAT policy, the security appliance translates the address. If packets do not match a policy, they are sent out without being translated. Some organizations mandate that a translation policy be defined before hosts can send traffic through their firewalls. To meet that requirement, you can enable the NAT control feature on the security appliance. If implemented, any traffic trying to pass through the security appliance without an address translation policy is dropped. Even if you do not want to translate an address, but the NAT control feature is turned on, you must define a policy to bypass address translation. Table 4.1 discusses the NAT behavior with or with the NAT control feature when traffic is originated from different security level interfaces. So traffic direction, NAT control disabled, NAT control enabled. From lower security level interface to high security level interface, or from high security level interface to low security level interface. No address translation policy is required for translating the inside IP address. If traffic matches a policy, address is translated based on the configuration policy. Address translation policy is required for translating the inside IP addresses. If traffic does not match a policy, address is dropped by ASA and a log message of 305005 is generated. Between same security level interfaces, no address translation policy is required. If traffic matches a policy, address is translated based on the configuration policy. No address translation policy is required. If traffic matches a policy, address is translated based on the configured policy. Packet flow sequence. When a packet passes through an appliance configured for address translation, the following sequence of events occur. Step 1. The packet arrives at the ingress interface from the end host. 2. The security appliance checks to see whether the packet is part of an existing connection. If it matches an existing connection, the processing function skips to step 4. If the packet is not part of an existing connection and the packet is the packet in a flow, for example, a SYN packet for TCP, the packet is evaluated against an inbound ACL applied on the ingress interface. Step 3. If the packet is allowed in, the security appliance first checks to see whether a translation with a global IP matching the destination of the packet exists on the interface where the packet is received. A quick route lookup is done only to determine egress interface. If there is a match, the packet is virtually forwarded to the interface of the translated address, skipping the global routing table check. If there is no translation matching the destination IP of the packet on that ingress interface. Step 4. If address translation is enabled and the packet matches the translation criteria, the security appliance creates a translation for the host. Step 5. On the egress interface, the security appliance consults the routing table to ensure only routes pointing to the egress interface are eligible. Step 6. The security appliance creates a stateful connection entry for TCP and UDP packets. The security appliance can optionally create a stateful connection entry for ICMP traffic if ICMP inspection is turned on. Step 7. On the egress interface, packet is transmitted on the physical interface. Security protection mechanisms within address translation. Address translation not only masquerades the original IP address, it also provides protection against TCP connection hijacking for hosts with weak SYN implementation. When a packet enters the higher security interface and is destined for a lower security interface during the TCP three-way handshake, the security appliance randomizes the original sequence numbers used by the hosts. This process is illustrated in figure 426. When the host 192.168.10.10 sends a TCP SYN HTTP packet to a host 209.165.201.1 with an initial sequence number ISN of 123456788, the Cisco ASA changes the source IP address to 209.165.200.226 and also modifies the ISN to a randomly generated value of A1B2E3C4. So in some deployment scenarios such as BGP peering with MD5 authentication, it is recommended to turn off the randomization of TCP packets. When two routers establish BGP peering with each other, the TCP header and data payload are 128-bit hashed using the BGP password. When the sequence number is changed, the peering router fails to authenticate the packets because of the mismatched hash. Cisco ASA also provides protection against certain types of denial of service DOS attacks by using the embryonic and maximum connection limit. The security appliance can restrict the establishment of new connections to the inside servers. An embryonic connection is a half-opened connection from the client to the server during the TCP three-way handshake. When the number of embryonic connections hits the maximum allowed limit, Cisco ASA starts intercepting the SYN packets from the client to the servers. This process of intercepting the TCP packets is also known as TCP interception, as illustrated in figure 427, and consists of the following 7 steps. 1. The client sends a TCP SYN packet destined for the server. 2. The security appliance responds with an ACK on behalf of the server. 3. The client, if legitimate, acknowledges the receipt of the previous packet. The security appliance marks the connection as valid. Step 4. The security appliance sends a TCP SYN packet destined to the server. Step 5. The server responds with an ACK to the security appliance. Step 6. The security appliance acknowledges the receipt of the previous packet and joins both connections transparently without any user interception. Step 7. The client and the server pass data traffic. And so I'm going to leave it here this evening for this video. If you like listening, please consider like, sharing and subscribing. Thank you.